Welcome to Module 8 on nanotechnology. We've got a few administrative things to take care of first. The first is I'd like you to go through the gradebook and look for any zeros or any places where a work that you've turned in, perhaps late, you didn't get credit for. Okay, so please look through there, make sure that you get credit for everything that you've done. I'll check, but hey, I mean, two sets of eyes are better than one. The second thing is that you're going to get a course survey. I would really appreciate if you took the time to take the course survey. You'll get a link. You'll have to log in with your student ID, and you'll take the survey. I don't get to see the results. I don't get to see the results until long after your grades have been submitted, so it can't affect your result, your grade. I won't even know if you've taken it or not. I'm asking if this course has been of any value to you. Please take 5 minutes to go over and take the exam. Okay, so on to nanotechnology. Why would we want to make things smaller? Well, the first is that it uses less material. If we want to live have a more sustainable society, it would behoove us to use fewer materials. A lot of our processes, for instance, a chemical process, catalytic process, take place on the surface of another material. If you can grind that material up very finely, then you increase the surface area. I mean, that's what happens in a grain elevator. You know that you can take grain, you can eat it, and your body can burn those calories, those chemical bonds, for fuel for your body. Well, grain dust is very, very finely ground. It's in contact with oxygen, and it can burn very rapidly, much more rapidly than it would burn inside of your body. Okay, as a matter of fact, they call them grain elevator explosions. There are other substances you can do this. I'm sure you can find a YouTube video. I don't recommend trying it. It's incredibly dangerous. Please don't do it. But those reactions happen very quickly when you have a lot of combustible material in contact with a lot of oxygen. Let's see, what other examples do we have? Size-wise. When we get down to the nano size, we're getting down to the scale of atoms. Now, if we take a look at macroscopic objects, the quantum wavelength associated with an object is inversely proportional to its momentum. Its mass and its velocity. Okay, so that's expressed macroscopically as its mass and its velocity. The quantum wave associated with myself is inversely proportional to my momentum. Whatever momentum I have moving my head or moving around on the planet, around the star, that wavelength is incredibly small, and it simply doesn't interact with normal matter. It's way below the size of atoms, and so it simply doesn't interact with those atoms. Now, if we get down to the size of an atom, we have something that has a wavelength that's about the size of the object it's associated with. And that gives us an effect where the quantum wave associated with an atom or an electron begins to interact with the particles that surround it. They're about the same size. So, we begin to see things like quantum interference. So we can come up with new properties of materials at the nanoscale that we don't see at the macroscopic scale. And so there's two real different approaches. Occasionally you'll run across, as you're doing your research, you'll run across these doomsday scenarios, like it's called the gray goo scenario, where somebody builds these self-replicating machines that are down at the molecular level, and they proceed to disassemble the entire world and turn it all into little molecular machines, other little molecular machines, turning everything into a gray goo. Well, that requires a lot of energy and a lot of information, and it's been shown to be thermodynamically not stable, and so it's not really a concern. So you can kind of pass by that one. In any case, I look forward to your comments in the discussion board, and please remember to take the survey. Okay? Have a wonderful last week.